Okay, so I'd like to see if you have any, well, of course, you can ask about what we did this week in the previous part, but I'd like to see your opinion on these multiple choice. So which option you deem to be correct? They are exactly the one I gave you a couple of hours ago. Okay, so we have one suggestion here, but only one. So that's good to have one suggestion at least, but I'd like to have a little bit more. So what are we given here is a map from R3 to R33 to R33. So we are sending 3 by 3 matrices into 3 by 3 matrices by performing this trick. So we take the matrix, we take the transpose, and we sum them. Okay. Of course, you can write down these in coordinates. So you can say, well, I take matrix A, B, C, D, and so on with 9 entries and compute what is the image of that. You can also go and get your hands on the associated matrix, but it's probably not the best idea. So one thing you can do is choose basis. Why not, the usual basis with only one element different from 0, right? So you can pick these 9 elements here and compute the associated matrix. And then once you have the associated matrix, well, you can have a look to the kernel of M. You can have a look at the eigenvalues, eigenvector. Of the matrix. So you can play quite a lot of game. You can look at the column space of the matrix, and all of these will give you information about the map. But this is not the recommended way because it is a little bit cumbersome. You have to work quite a lot. So an easier approach when you have this kind of map which are not given explicitly in coordinates is to think. So what I recommend you is to use properties of F. So use the definition of F. So it is sometimes hard for you, especially at the beginning, to do things without computing much because what is the easiest thing to do is to learn algorithms, right? To learn procedure, to learn a machinery that will give you the answer. That's fine, that you can do, but it is not always the best way. Sometimes it is best to think and to use more theory and less computations. So for example, here, let's say we want to say something about the kernel of F. Okay, so let's do this together. So I just write here again, F goes from matrices 3 times 3 into matrices 3 times 3. Just bear in mind that if you compute the associated matrix, it's going to be huge, 9 times 9. So when you go for the eigenvalues, well, the characteristic polynomial will have degree 9. And so computing the roots can be difficult, and it's also easy to make mistakes while computing that degree 9 polynomial. So you see why the computational approach is not probably the best. And how is the map defined? Well, carries A into A plus its transpose. So what is the kernel of F? Well, the kernel of F is given by all matrices such that A plus A transpose is 0. And now you can immediately tell me what is the kernel. What kind of matrices are in the kernel? There is a name for these matrices, a name that now you should know very well. What kind of matrices do you find in the kernel then? So let me know in the chat. So skew-symmetric matrices, that's true. So the kernel is given by skew-symmetric matrices, 3 by 3 matrices. And so I can write them down explicitly because I know how they look like. So first of all, on the diagonal, they have 3 zeros. And whenever I put a number here, like A, I will put minus A there. When I put B here, I will put minus B there. And when I put C here, I will put minus C there. So that A, B, and C are real numbers. So now you see, I found the kernel completely. And so what is the dimension of the kernel? Sophia Kornalk got it correctly. It is 3 because I have three parameters, so cannot be more than 3. So this is telling me that the dimension of the kernel is less or equal than 3 because I have 3 parameters. And it is exactly 3 because if you compute the matrices by setting A equal 1, B and C equal 0, and then B equal 1, A and C equal 0, C equal 1, and what is that? A and B equals 0. So these will produce 3 matrices. So M1, M2, and M3, which are linearly independent. So what I mean by producing matrices, that matrix, for example, M1 comes by going here and putting A equal 1, B equals C, B equals C equals 0, and so on. And they are linearly independent. So the dimension of the kernel is actually equal 3. So this is telling me that the dimension of the kernel is actually 3. So dimension of the kernel of F is actually equal 3. And let me just raise this a little bit. Yeah. Okay, so we got that the dimension of the kernel is equal 3, and so we got that this is true. This option is correct, is the right one. So this is true. Okay, any doubt, question, or remark before we go on with this? Because now I'd like also to go and show to you. I'd like to go and show to you why the other options are not correct. So let's do this. So any doubt, question, or remark? Good. So Alireza says, why B cannot? Well, it's not a matter of cannot be true. Alireza, here is a matter of not being true because the map is explicitly given. So, you know, either it is true or it is false. So, for example, to decide about B, you need to, so B is true if and only if the dimension of the image is the dimension of R33. So what is the dimension of R33? Can you tell me? Yes, it is 9. And the Albicina has a nice idea. It says the map does not cover matrices that are not symmetric, so it will not cover all R33. That's a very nice remark. So let's make a note. The note is that f of A is equal A plus A transpose. And this is a symmetric matrix. Symmetric 3 by 3. So the image of F is the set of A in R33 such that A is equal to A transpose. And this is strictly contained in R33. So this means that F is not surjective, which means that the image of F is not R33, if you want. And this means that B is false. So this is one way of doing this. Another way is to note that to have B, you must have the dimension of the image equal 9. But we have the rank nullity theorem telling me that the dimension of the image plus the dimension of the kernel must be equal to the dimension of the starting space, which is 9. So this is 9 also. And so this means that this is 0. But we know that the kernel has not dimension 0, and so we get a contradiction. Well, so we get that it's not possible for B to be true. So, but dimension of the kernel is 3. Thus, B is false. And so we can say it here, B is false. Okay? Any other question, doubt, or remark? And similarly, we can go through the other options. It's a good chance for us to learn something new and see that they are false. So, for example, what do you think of option C? So what do you think about option C? Of course, should be false, must be false, because there is only one true alternative, right? But why is it false? So let's go here. You see, this is very, very easy to check, because this is saying that a given matrix is not an eigenvector. So what does it mean to be an eigenvector of F? Well, being an eigenvector is equivalent to the fact that F of E3 is equal to a multiple of I3, sorry. So is equal lambda I3. So being an eigenvector means that F of I3 is lambda of I3 for some lambda, right? So can you compute for me I3? What do you get? So you see, you don't have to go and compute the eigenvalues and compute the eigenvectors. It's just to substitute. And Paolo Lovera says, well, look, this is 2I3. So you see, the problem is that I3 is an eigenvector. So this is false because it says it is not. Again, no need to compute, just need to think and remember. Finally, F does not have real eigenvalues. Well, this is clearly false. Here is a real eigenvalue. For example, 2. Can you tell me another real eigenvalue? Can you tell me another real eigenvalue of F? If you look at part A, you should immediately spot one. Zero, exactly, because it is not injective. So also 0 is an eigenvalue of F. Then there could be the question, are there more? What are the other eigenvalues? Well, that's a different story. But for the time being, it's very easy to see that these two are eigenvalues, and so option D is false. Okay, so now let's play the same game. If you don't have doubts or questions about this one, let's say we play the same game for this one here. So we are given a linear map through the images of elements of a basis of R2. So this linear map goes from R2 into R2. Here is what it does. And now we want to decide whether it is or not injective, surjective, preimage of 3,3, and kernel. So maybe you didn't have time to work on this before our lecture because you were busy with another lecture. So I give you, say, 4 minutes. Think about this. As soon as you have some ideas, you can use the chat, and then we'll discuss it together, okay? So a couple of minutes more to see what you think. Of course, it's also possible to say, I have no idea how to do this. that's fine. You should know how to do this, but we are here to learn. So wait a couple of minutes more. I'd like to see some options. Okay, so we have Sofia Karnauk and Federico Moro, very unsure. Maybe it is A, maybe it's not. Well, I understand. Then we have someone suggesting D, A, and so on. Okay, so how do you deal with these maps? Again, there is a computational way. So computationally, I would say find F explicitly. Which it means for me, write down F of xy equal to something, okay? And how do you do this? Well, in order to do this, you need to use the canonical basis. E1, E2, because xy is just x E1 plus y E2. So if I want to compute, well, let's do like this. So if I want to compute f of xy, so to find the formula, this is going to be x f of E1 plus y f of E2. So what I need to do is to compute f of E1 and f of E2. Just remember that these are 1, 0, and 0, 1. That's the usual thing. So what I need to do, since I know f of 1, 2 and f of 2, 1, I need to write down E1, which is 1, 0, as a linear combination of 1, 2 and 2, 1. This is done solving a linear system. Okay, now you don't need me to show to you how to solve this linear system. In this case, it is kind of easy to see that if you sum these, if you take this vector and say subtract twice of this, you will get something which is very close to 1, 0. Okay, so what I want to say is that if I take 1, 2 minus, say, twice 2, 1, well, this is unreadable. So let's say probably red is better. So let me say this. I try to solve the system being smart. So I subtract 2, 1, and what I get is 1 minus 4, which is minus 3. Then I get 2 minus 2, which is 0. So I get minus 3, 0. So if now take this vector here and multiply by 1 over 3, I will get 1, 0. Do you agree? So do you agree with me about this? Okay, so once I have this expression, I can easily compute f of E1, because then f of E1 is minus 1 over 3 f of 1, 2 plus 2 over 3 f of 2, 1. And now we go and see 1, 2, and 2, 1 are just exchanging. So what I get is minus 1 over 3, 2, 1 plus 2 over 3, 1, 2. And so if I compute, what I get is minus 2 over 3 plus 2 over 3, which is 0. And then I get minus 1 over 3 plus 4 over 3, which is 1. So you see E1 goes into E2. And now I have to compute f of E2. And to compute f of E2, I need to go back here and say, now I want to express E2 using 1, 2, and 2, 1. Okay, let's do that. So to compute this, I need to say, well, I want to express E2 as a linear combination of 1, 2, and 2, 1. Again, you can compute these by solving a linear system of equations, or again, say, trying to be smart and say, well, if you take 1, 2, now we want to kill the first one, minus 2, 1, 2, plus 2, 1, what we get is 0, minus 4 plus 1, minus 3. So again, if I multiply by minus 1 over 3, so 2 over 3, 1, 2, minus 1 over 3, 2, 1, I will get 0, 1. And so this tells me that f of E2 is equal to 2 over 3 f of 1, 2 minus 1 over 3 f of 2, 1, which is 2 over 3, 2, 1 minus 1 over 3, 1, 2, which is equal to 4 over 3 minus 1 over 3, 1, 2 over 3 minus 2 over 3, 0. So this is E1. Okay, so what does this tell me? Well, this tells me that f of x E1 plus y E2 is just equal to x E2 plus y E1. So if you want, f of xy is equal yx. So this is the map that it is given to us. You see, it's computing, but it is not terrible. It's just something we can do by solving linear system of equations. Okay, now, if you want to go and look for the kernel of this one, for example, so we are looking for pairs xy such that yx is 0, 0. And so you see the kernel is just 0, 0. And so this means that if you go back, the first option, yes, it is injective. Nothing strange about that, right? It is injective because the dimension of the kernel is 0. Also, something you want to note, F is an endomorphism. It means that F is injective if and only if F is surjective. And this comes from the rank nullity theorem. So endomorphism, because you go from R2 into R2, then being injective is equivalent to be surjective. Why? Well, simply because of the rank nullity theorem. Dimension of the kernel plus dimension of the image equal 2. So you see, if the kernel has dimension 0, then the image has dimension 2. So if it is injective, it is surjective. And if it is surjective, it is injective, because if the image has dimension 2, the kernel has dimension 0. That's always true for endomorphism. So since A is true, F is also surjective, and so B is false, right? Then, for example, how do you check if F minus 1 of 3, 3 is equal 1, 1? Well, this is true if and only if F of 1, 1 is equal 3, 3. But if you compute using what we have here, this is telling me that f of 1, 1 is 1, 1. So this is an eigenvector, right? So it's not 3, 3. And so you can say that D is false. And finally, we are saying that the kernel is this one. Well, this means that f of this is 0, f of this is 0, and the kernel has dimension 2. So we know this is clearly false. Okay, so this is how you can solve this exercise by computing quite a lot. However, we can be smarter than this. So I show a quicker way, which requires more thinking and less computing. However, before doing this, let me know if you have doubts or questions about what we did. Okay, seems like everything is in order. So how you can do this computing less? Well, it can be done. Oh, sorry, I didn't add the page. So I want a new page here. And for some reason, okay, no. Maybe I have to add it here. Let's see. Let me try one more. Add a page. Okay, now it is not working. Okay, so I want an empty page here. Okay, now I have the empty page. Well, last try, add a page. Okay, well, doesn't want to play. Okay, so how can we do this more explicitly? So how can we do this more explicitly? So what I do is move this to the next page. So I got the empty page I was looking for to say how we can do this thinking more. So the idea is the following. I can choose as a basis of R2 this one. So this is a basis. And then I can choose the same basis for R2. So I choose these bases for R2. And then I consider the map F, which I know sends 1, 2 into 1, and 2, 1 in 1, 2. So what is the associated matrix to F with respect to this choice of bases? Can you tell me what are the columns of this matrix? So let's call this V1 and this is V2. So the first column comes from F of V1 and the second column comes from F of V2. So what is F of V1? Okay, Tiarmush is writing the matrix because the first column is what? F of V1 is V2, which means is 0 V1 plus V2, 1 times V2. And so you remember, you have to use these two numbers to make the first column, 0, 1. And since f of V2 is V1, so 1 V1 plus 0 V2, the second column is 1, 0. So we obtain this matrix. And from these, we see that the dimension of the kernel of F is equal to the dimension of the kernel of the matrix, which is clearly 0 because the matrix is invertible. And in this way, you can immediately see that option probably A was correct, because then it is injective. This is telling you also that option B is false, that option D is false, that option D is false. About option C, it was just a matter of checking and remembering what is the pre-image. Okay, any doubt, question, or remark? Okay, so if not, let's move to the last of these multiple choices. So we are giving a huge matrix with real coefficient satisfying that property, and we want to find the correct statement about the inverse of A20, about A having or not real eigenvalues, about the fact that 1 is an eigenvalue, about that A20 is not invertible or not. Looks strange, looks weird, but it is not, you will see. It is something you can actually do with what we learned by thinking, not computing much, but thinking, okay? So what do you think? Federico Guglielmi says, can we also say that the image is f of 1, 2, so it's spanned by f of 1, 2 and f of 2, 1? Yes, you can say that because the image is the linear span of the images of a basis. So that's true. Since 1, 2, and 2, 1 are a basis, you can use that to say precisely what the image is. You are correct. Yeah. So let's write it here as a note. The image of F is the linear span of F of 1, 2 and F of 2, 1, since 1, 2, and 2, 1 is a basis. Of R2. Okay, so we have some people suggesting option C to be true. And what is the only thing happening here? If you have this expression, the most natural thing to do is to note that A20 times A minus the identity is equal to A21 minus A20. And we are saying that this is 0. So this means what? This means that the 0 matrix is a product of these two matrices, which means that the determinant of A20 times the determinant of A minus 1 must be equal 0. So what is this saying? So we know that this product is the zero matrix. By Binet formula, we have a connection with the determinant. Okay? So what we see at this level here is that matrix A20 is not invertible because there is a matrix multiplying it into the, sorry. I'm saying something stupid. I'm looking at option A. So option A, we are saying the inverse of A20 is A minus 1, not true, because the product of A20 by A minus 1 is not the identity, but it is 0. So this is false. Okay, good. Then let's look at the second one. We know that either the determinant of A20 is 0, or the determinant of A minus 1 minus the identity is 0. And this one implies that 1 is an eigenvalue. And this one, if you think about this, implies that the determinant of A is 0, and so implies that 0 is an eigenvalue. So what we know is that either 0 or 1 is an eigenvalue. So option A is false. Does not have real eigenvalue is false. Okay. Then let's see the next one. 1 is an eigenvalue of A, and A20 is not invertible. And I'm afraid that here, this multiple choice has a problem because these two might be both true. Because you see, what is missing here is it is necessarily true that. Otherwise, anyway, written in this way, this is false because the product is 0. This is false because, of course, there are two real eigenvalues. 1 is an eigenvalue of A. Well, it depends because maybe A is the 0 matrix. So maybe this part is true and not this part, and vice versa. So the problem is that these two are both false. So there is no true option in this multiple choice. So there is a mistake. I'm sorry, I didn't realize it. So they are all false. So why C is false? Because A could be equal 0, and then it satisfies this situation here, but 1 is not an eigenvalue. Or A could be the identity matrix, right? And so satisfy the red box equation, but it is invertible. So we cannot say that either of the two is true. So there is some twiggling to make. So probably at the beginning in the text, there should be something, let A be a non-zero matrix, okay? But for the way it is written now, they are both false. Okay, any doubt or question? Oh, thank you. That's my bad. I didn't notice here. So here is saying that it cannot be the zero matrix. Thank you. Thank you. So thank you who was helping me out of this. It was Pascal Ariaki. I made a typical mistake, not reading the multiple choice completely. So this one cannot happen, right? cannot happen because A is invertible, right? So the only option is that 1 is an eigenvalue. So thank you. This is true. And A is not invertible is false because A minus 1 to power 20 is the inverse of A20 power minus 1. So thank you, Pascari. I simply did a stupid thing, not read the multiple choice, the row fill carefully enough. Thank you. Okay, now everything is fitting nicely. Any doubt, question, or remark? So being a invertible, the determinant cannot be 0. So all is good. Okay, so if you don't have doubts, questions, or remark about these multiple choices, what we do now is go through some of the exercises in the exercise sheet we have. So we can probably spend some time practicing. So this is going to be LAG X, I think 1920, right? This is what it should be. So let's try one of these exercises, probably from the first part. So X10.1. And let's say we want to find compute the eigenspaces of, and let's see a couple of matrices. So something like this, maybe these cross-looking matrix, so X-shaped matrix. Let's start computing the eigenspaces of this one, okay? So let's see what you think about the eigenspaces of these matrix here. What are the eigenspaces? So it's probably a good idea to start thinking about the eigenvalues and then to go through the eigenspaces. So there are two easily spot eigenvalues, right? One is 0 because the determinant is 0. So 1 is 0. Means that the lambda equal 1, so lambda 1 equals 0 is an eigenvalue. And since there is this cross shape here, you can see that 1 is an eigenvalue also because the determinant A minus the identity will be the determinant of a matrix with 0, 0, 1, 0, 0, 0. You see a 0 row. So it's going to be 0. And so lambda 2 equal 1 is an eigenvalue. Right? But in principle, since the dimension is 3, we could be missing one eigenvalue, right? And actually, some of you found the eigenvalue which is missing, which is 2. How can you find it? Well, you compute a characteristic polynomial and you solve it, finding the roots. Sometimes it's useful to know some of the eigenvalue because then you can apply the division theorem to make your computation easier. And probably the remark that some of you made is that if you multiply like this, you will get 2, 0, 2, which is twice 1, 0, 1. And this means that lambda 3 equal 2 is an eigenvalue also. So you see, we have lambda 1, lambda 2, lambda 3, 3 distinct eigenvalues. And this means, for example, A is diagonalizable, right? Because since they are distinct, it means that the multiplicity of each lambda I is equal 1. And so the criterion we saw yesterday is trivially satisfied. This is just a side remark that we make. Now we need to go and compute the eigenspaces. So for example, E0 is just the kernel of A. It must have dimension 1 because this means the dimension of E lambda I is always equal 1. So each eigenspace has dimension 1. So I just need to find a element in the kernel, and that's easy. Just take 1, 0, minus 1. Similarly, you see, here I have a non-zero element in E2. So that's again a basis because also E2 has dimension 1, right? So the only one we have to look for a second to is E1. So the kernel of the matrix I wrote here. So this 0, 0, 1, column of 0, 1, 0, 0. And this is the linear span of 0, 1, 0. So we computed all the eigenspaces of this matrix without any special effort, right? We just look at the matrix, then take the characteristic polynomial, very easy to find the roots. There are 3 distinct roots, so each eigenspace has dimension 1. Just pick one non-zero vector there, and you are done. Any doubt, question, or remark about how we did this? If not, we will just consider a similar, but for a different matrix. So say this matrix A, which I now write. So 1, 1, 2, 0, 0, 0, and then say 0, well, maybe say 1, 0, 0. So what can you tell me about the eigenspaces? Well, first, you have a look to the eigenvalues. It should be very easy to compute, find them, and then we can go and look at the eigenspaces. So someone asked about getting E lambda 3. Well, in this case, it was just by this observation. This is what produced lambda 3, but the method is to solve px equals 0. It is a degree 3 polynomial of which you know already one root because you know it is true that 0 is an eigenvalue. So it's very simple then to the other two roots because the degree of the characteristic polynomial is 3. Okay, now let's think about the eigenspaces of A. So first, what are the eigenvalues and how do you find the eigenspaces? So Ashbairagi says, well, the trace is the sum of the diagonal elements and of the matrix, and the determinant of the 3 by 3 matrix is the determinant of the 3 by 3 matrix. What we will see is that the determinant is the product of the eigenvalues, and the trace is related to the sum of the eigenvalues. But this is something we are going to see in the future, okay? Probably next week, we'll speak about the relation between trace and determinant and the eigenvalues. But there is a relation, there is a connection, not difficult to find, but we will investigate it. So for example, since this is a triangular matrix, we have eigenvalues lambda 1 equal 1, multiplicity of 1 is 2, and then lambda 2 equal 2, multiplicity of 2 is 1. So this is what we have here. Right? And if you note, the determinant of A, so just a quick note of what we will see in the future, the determinant of A is 1 times 1 times 2. So it is lambda 1, lambda 1, lambda 2. So it's the product of the eigenvalues. And the trace of A is just 1 plus 1 plus 2. So it is lambda 1 plus lambda 1 plus lambda 2. So what is going to be always true is that trace and determinant have a connection with the sum of the eigenvalues and the product of the eigenvalues. That's always true. Okay, so these are the 3 eigenvalues of matrix A. So now we know that the dimension of E lambda 1 is less or equal than 2, and the dimension of E lambda 2 is less or equal than 1. So this means that the dimension of E lambda 2 is exactly 1, because it is always at most 1, right? So to compute E lambda 2 is in some sense easier, because we just need to look at the kernel of the matrix you get by subtracting 2, so minus 1, 0. And we just need to find one linearly, well, non-zero vector, which is this one. So here is a basis for E lambda 2. Only one is needed. Then when you go and look at E lambda 1, you need to go and find the kernel of the matrix 0, 0, 1, 1, 0, 0. And you see, since this matrix has rank 2, it means that the dimension of E lambda 1 is 3 minus 2. So it is again, well, is 3 minus 2, which is equal 1. So again, only one vector suffices to find the basis, and here it is, 1, 0, 0. And since the dimension of E lambda 1 is strictly less than the multiplicity, this means that the matrix A is not diagonalizable, right? Because it's not true that the dimension is equal to the multiplicity for all eigenvalues. Okay, any doubt, question, or remark? Okay, so if not, we move to another exercise. So we want to find the eigenvalues. So compute eigenvalues and eigenspaces for the linear map f xy equal yx. So let's see what you do about this. So let me know when you have the eigenvalues so we can keep going on together. So Cesare Piemontese suggests as eigenvalues plus and minus 1. So how do you compute the eigenvalues? Well, by using the definition, if you want, or using the associated matrix. So let's say we pick canonical basis of R2. Because F goes from R2 into R2, right? So one way of finding the eigenvalues and the eigenvectors is to write down the associated matrix with respect to the same basis in the starting space and in the target space. Okay? And these bases we have, so we just to write down the two columns, which is what we did before. So I have to write down f of v1, which is 0, 1, and f of v2, which is 1, 0. So here is the associated matrix. So I can write down the characteristic polynomial as the determinant of m minus x, the identity. So the determinant of this matrix here. And so I get x squared minus 1, which factors as x minus 1, x plus 1. And so we have the two eigenvalues, lambda 1 equal 1 and lambda 2 equal minus 1, the eigenvalues. And this is what, for example, Cesare Piemontese produced. Okay, you can also argue in another way, trying, as I told you, to be smart and devise what are the eigenvalues and eigenvectors by the definition, because as a remark, what is this map doing? It takes f of xe1 plus ye2 into xe2 plus ye1. So you see that if x and y are equal, you will get the same image. If they are opposite, you get opposite, which is basically what we produce here. And then Sofia Carnot produced the eigenspaces. So just let's see that since lambda 1 is different from lambda 2, it means that f is simple. So say f, let's say, is a simple endomorphism, or f is simple, because the associated matrix is diagonalizable, right? And so that's the definition of simple endomorphism. Just make this remark. So it means you can find the basis of R2 made by eigenvectors of F. So let's have a look to E1 and to E2. So what are they? Well, the kernel of M minus the identity. So the kernel of minus 1, 1, 0, minus 1, sorry, 1 minus 1. So it is the linear span of 1, 1. And here, the eigenspace of minus 1 So the kernel of the matrix filled up with ones. So the linear span of 1 minus 1. Here are the eigenspaces, and here are their bases. Okay, any doubt, question, or remark about this? Okay, let's do something less explicit to see again that sometimes only computing is not going to be the best way. So let's say we have f from r to x into r to x, sending the polynomial p of x into its first derivative. And let's say we want to compute the eigenvalues and a basis for the eigenspaces. Of f. So let's see how you do this, okay? So how you manage to work in this case. Okay, so Sophia Carnot found an eigenvalue. And before going and computing, let me tell you again, there are two methods. One method is choose a basis, like this one, 1x and x squared. compute the associated matrix, compute eigenvalues and eigenvectors. And eigenvectors. So it is a 3 by 3 matrix, so it's manageable, but it is not the easiest thing to do. Or the other approach is use the definition. So use the definition of F. So basically use more theory, think more about what you are doing. So what I mean by this, F of a polynomial is the first derivative of the polynomial. So for example, for sure, 0 is an eigenvalue because there are polynomials having derivative 0, and they are the constant polynomial, right? So this, for example, tells me that lambda 1 equals 0 is an eigenvalue. And it also tells me that E of 0 contains the linear span of 1. What is this? Well, this is just the constant polynomial. Constant. Because they have 0 derivative. Or what can we do more systematically? Well, what we can do is saying that P of x is an eigenvector with respect to lambda if and only if f of p of x is lambda p of x, but this is p prime of x. So we are looking for polynomials such that their first derivative is proportional to the polynomial itself. So what you do is say, well, p of x is a polynomial in x of degree at most 2. So it means that p of x can be written as ax squared plus bx plus c. And so this means that p prime of x is just 2ax plus b. So this is telling me that 2ax plus b must be equal to lambda ax squared plus bx plus c. Okay? And so what do we see here? Well, we see that 2ax plus b must be equal to lambda ax squared plus lambda bx plus lambda c. And you see, this is an equality of polynomials. So to find the eigenvectors, I need to find polynomials satisfying this property. So basically, I want that the difference is the 0 polynomial. So I want lambda a squared plus lambda b minus 2ax plus lambda c minus b is the 0 polynomial. Is the 0 polynomial. And to be the 0 polynomial, we know that all the coefficients must be 0. So this happens if and only if lambda a is 0, lambda b minus 2a is 0, and lambda c minus b is 0. And you see, this happens if and only if lambda is equal to 0, or lambda is different from 0, and a is 0, b is 0, and c is 0. So if lambda is different from 0, you get the 0 polynomial. which cannot be an eigenvector. So this is saying that P of X is the zero polynomial, not an eigenvector. So what happens if lambda is different from zero? There are no eigenvectors. So eigenvectors only exist if lambda is equal to zero. So what is the conclusion? Hence, lambda equals zero is the only eigenvalue. And this means that the multiplicity of 0 is 3, since f goes from R to X into R to X, and the dimension of R to X is 3. And what is the eigenspace of 0? Is exactly the space of constant polynomials. So it is not simple, because the multiplicity of the eigenspace is not equal to the multiplicity of the eigenvalue is not equal to the dimension of the eigenspace. Okay, so you see, we have one way of solving this, which is by using the definition and thinking more. And we get exactly what are the polynomials, which are eigenvectors, and the possible value of lambda to be eigenvalues. Okay? Or, as we said at the beginning, you can follow procedure 1, which is compute the associated matrix with respect to the bases 1, x, and x squared, which means we go and get this 3 by 3 matrix by computing the 3 columns. So column 1, f of 1, then you compute column 2, f of x, and you compute column 3, f of x squared. So f of 1 is 0, so you put 3, 0 here. F of x is just 1, which is 1 plus 0x plus 0x squared. So we get 1, 0, 0. And f of x squared is 2x, which is 0 times 1 plus 2 times x plus 0 times x squared. So it is 0, 2, 0. And you see that the characteristic polynomial is p of x equal minus x cubed. So, and this is how probably Sofia Carnot produced the answer about eigenvalues and multiplicity. Okay, any doubt, question, or remark? Okay, if not, we can call it a day and meet again next week. Please take your time to revise all these notions and ideas. If you have questions, I will be here monitoring the chat. Okay, so if we don't have questions, have a nice week. Okay, so looks like you don't have questions or anything, so we meet again next week.